Welcome. We're going to have 4 speakers. Our first talk is about state space estimation for DPOR-based model checkers, and the speaker will be Minjian from the University of Illinois.
Hello? Okay. So good afternoon. I hope you all enjoy your lunch. I will be giving this talk on counting traces. This is a joint work with Mohammad, Bala, and Rupak from MPI, Umang Mathur from National University of Singapore, and myself from UAUC. Okay, so let's start with this very simple concurrent program, which have 2 threads and 1 shared variable. The first thread just reads 3 times from variable x, and the second thread performs 1 read. And we know there are basically 4 possible schedules depending on the position of the read from the second thread. But at the same time, we know that the 4 possible schedules collapse into 1 program behavior because they are concurrent, they're independent and concurrent. Namely, all the read from the same initial value. And one popular way to reason about program execution equivalence is Mazurkiewicz equivalence, which basically identifies executions that differ only by commuting non-conflicting events. 2 events are non-conflicting or independent if they access different memory locations, or they are both read. A DPOR-based stateless model checker is an algorithm that systematically explores all the Mazurkiewicz classes induced by a concurrent program. The goal is to check whether any execution may fail a certain program assertion or run into deadlock or data race. Typically, DPOR-based model checkers guarantees to explore or cover all the Mazurkiewicz classes, which means that they explore at least 1 execution from each of the Mazurkiewicz class. So in practice, there are 2 questions that is specifically related to the model checking progress. The first question is basically how long does it take for my model checker to finish? I would like to know, does it worth it at all to run the model checker on a concurrent program? And if so, how much time I would like to allocate? The second question is that if I run my model checker for a fixed time budget, and it didn't finish, I would like to know at least how much of the search space is covered. Our approach to address the 2 questions is to look into this mathematical problem, which is a counting problem. The problem asks for a given program instance P with an execution bound, which means that we assume every execution can have at most B events. We want to count the number of different Mazurkiewicz classes induced by the program. So the rest of the talk is organized as the following. I will give a very lightweight discussion on the hardness result. Then I will be introducing our first estimator, which is designed on a DAG model. Then I will be talking about the second estimator, which is designed on the tree model. And finally, I will be discussing the experiment and the evaluation. So first, we want to understand how hard is a counting problem. And in the paper, we show that under the assumption of sequential consistency, the counting problem is hard, even for programs with purely read and write events. Namely, we show that for the exact counting problem is Sharpie complete, even when one of the number of threads or the number of locations is constant. And a more negative result we showed is that approximation is also hopeless. Namely, there is no polynomial-time subexponential factor approximation exists for the counting problem unless P equals to NP. And this result also directly rules out the possibility of nice randomized algorithms, such as an FP-RAS, unless RP equals to NP. So given the hardness, we sort of lower our ambition. Our approach to solve the problem is to design the first unbiased estimator to estimate the counting. An unbiased estimator is a randomized algorithm which outputs a random variable whose expected value is a correct count. And in principle, if we run this unbiased estimator for sufficiently many times, the estimate will converge into the right value. And our hope is that in practice, the number of times we need to run for it to converge is reasonable. So our intuition in designing these estimators is to organize the Mazurkiewicz classes into nice graph models that we know how to estimate. So the first model we propose here is a DAG model. It is a very intuitive and almost naive model. Namely, for the very simple concurrent program on the left, we model it using the DAG on the right, where all the nodes represent Mazurkiewicz classes of prefixes of executions. And the edges in the DAG model are simply thread decisions. Like the red edge here basically means that the next event of the first thread is scheduled. And any path from the root to sink in the DAG is isomorphic to a program execution. And the more important thing is that in this DAG, the sinks represent the maximum Mazurkiewicz classes we want to count. So the next question is that how can we build an unbiased estimator to estimate the number of sinks of a given DAG? It turns out this is a solved problem by Leonard Pitt during his PhD at Harvard. So the algorithm is classic and simple. For a given inference to a DAG structure, what we need to do is to sample a random path from the root to one of the sink. Then the product of the ratio between the out degree and in degree along the path is going to be an unbiased estimation of the number of sinks in the DAG. But why is this algorithm usable on our DAG is not a trivial argument. We first need to argue that for a given program and this DAG model in our head, we will be able to sample a random path. In this case, it is actually simple because, as I said, every path in the DAG is isomorphic to a program execution. So to sample a random path, we just need to execute the program with some concurrency control, which allow you to proceed with one of the enabled thread at each time randomly. And as I mentioned, for the calculation uses the out degree and in degree of each node along the sampled path. So we also need to query the out degree and in degree in the program model. The out degree here is in some sense free because it is in the program model, it is just a number of enabled threads. The only question is that what is the number of in degrees along each of the node? And it turns out under the assumption of sequential consistency, we can query the in degree very effectively by maintaining a frontier of maximal event from each of the threads. So as a conclusion, to run Pitt's algorithm to draw one sample in this DAG model is going to take linear time and linear space. And this is our first unbiased estimator, but this is not enough for it to work in practice because this is just an unbiased estimator. We want to run the unbiased estimator for multiple times and hope that the value converges into the right value. And this means we expect the variance to be low. But unfortunately, this is very difficult. As we show it here with this simple program, we are just one thread read from a variable y, and another thread have n read from a variable x. The DAG estimator we propose here already results in exponential variance, while it only have one Mazurkiewicz equivalence class. This also means that the relative variance is also exponential. It means that the estimation is now going to converge in exponentially many rounds. Okay, due to the time limit, I'm not going to discuss the example in detail, but what we think is the following. For this example, which only has one Mazurkiewicz class, namely one sink, it already have exponential variance. If we can organize the Mazurkiewicz traces into a tree structure, then we will have zero variance because a tree with one leaf is just a path. And it turns out there is this model, which is defined by the state-of-the-art DPOR model checker, which is trust. So trust is a model checker that is optimal and stateless. It is optimal in the sense that it never explores two Mazurkiewicz class twice. So the search space of the trust algorithm is actually a tree. But it's important to notice that the search tree of trust is very different from the DAG model. In the sense, the first difference is that the edges here represent partial order decisions, namely like RF, like which right can this read be reading from, or coherence relation, like where I can put this right in between other rights. And any route to leave path in this tree is also no longer isomorphic to program executions, but they correspond to the trajectories of the algorithm's search procedure. And the only thing remains the same is that the number of leaves in this tree is still the number of maximal Mazurkiewicz classes we want to count. And to estimate the number of leaves for a given tree is a very classic program, and there is a very well-known algorithm by Knuth, which is we call the Knuth estimator. Many of you may have already realized that Pete's algorithm is just a generalization of Knuth's algorithm. It basically says that to estimate the number of leaves in a tree, I take a random path, and I take the product of the all degrees along the path. Okay, and this number is an unbiased estimate for the number of leaves. Then we need to argue why Knuth is usable on this trust tree. And the major difficulty or nuance is implementability. Knuth's algorithm requires us to be able to query, to sample a random path effectively. But this is not generally true for any search tree. The reason is that if the existence of the right subtree in this graph depends on the left subtree, we cannot really randomly sample a path without constructing the whole tree. But luckily, this is not the case for the trust search tree, because trust, as I mentioned, is stateless. Its exploration does not depend on its history. So it does not use exponentially many memory. Its exploration only needs the current stack. And the second thing we need to argue is that this tree is not in polynomial size of the program execution, and it's a classic result of the trust algorithm that the depth of the trust tree is at most in polynomial of the program bound. So to use Knuth's algorithm to draw one sample in this tree is still implementable in polynomial time. Okay, but unfortunately, even this tree can still be badly skewed. Namely, the variance can still be exponential for concurrent programs with only n+1 Mazurkiewicz classes. And this is a classic example which we call the hairbrush tree that is often referred to the people in statistics when they're trying to reduce the variance of the Knuth method. The lucky thing is just that the Knuth method is very popular, and there is an extensive study by people who are trying to reduce the variance. So we use this method called stochastic enumeration to reduce the variance. Okay, and evaluation is that we implement both of the estimators inside a Java model checker JMC. And the questions we want to answer in the evaluation are that how accurate are the estimates and what guidance can they provide about the model checking progress. We call our DAG estimator PASTER due to its Pete's algorithm, and we call the tree estimator TESTER. And the benchmarks we considered are standard concurrent data structures, such as a concurrent linked list, timestamp stack, and lower bound queues, etc. And as we count piece-right benchmarks, and some synthetic stress test benchmarks. In total, we have 42 program instances in the program, and with 30 of them, we have the knowing the ground truth. And the first observation we have in the evaluation is that the DAG estimator almost never converges into a meaningful value for all of our program instances, no matter how long we run it. But on the other side, on the other hand, our tree estimator tester has a better signal. So we run tester for 2-time budget, because this is our expected usage from us on our estimator. We run the estimator for a short time before we run the model checker to get an estimate. And we show that as a 1-minute estimate, 66% of the benchmarks, the estimation was accurate within the 80% to 120% bandwidth. And for the 5 minutes estimate, 75% of the benchmarks estimate was actually accurate. And then I also show some of the benchmarks which we do not know the knowing ground truth to see how can we use the estimate to interpret the timeouts. For example, so there is a concurrent benchmark we tested called course list. And we run the model checker for 1 hour. The model checker timeout after explore around 1 million Mazurkiewicz executions. And our estimator shows that the estimation was around 2 million. So even though our the model checker timeout after under the time budget, we know that it's covered around 50% of the search space, which gave me a level of confidence. But similarly, for the OPT list benchmark, the model checker again timeout after 1 hour after explored around 1 million benchmarks. But our estimator said that the total search space it has around e to the 8 many Mazurkiewicz executions, which means that what we have explored in 1 hour is very minimal. It means that we have very low confidence of what we have checked in the program space. Okay, thank you.
We have time for some questions.
Mm-hmm.
Can't come.
Thank you for the nice talk and nice results. So in the early part of the talk, you introduced this DAG model, and you mentioned that the number of sinks is equal to the number of Mazurkiewicz traces.
Yeah.
I didn't follow why that was the case. So can you give me, is it a quick proof or a quick intuition for why that is true?
No, this is just by definition, right? We define the nodes in the DAG to be execution graphs or Mazurkiewicz classes. That's why it's a DAG, not a tree.
Mm-hmm.
Namely, if two different prefixes actually reach into the same Mazurkiewicz trace, they will converge.
Okay, thank you.
Yes, thank you.
Any other questions?
Hi, thanks for the talk.
Thank you.
So I'm not an expert in model checking, but from the things that I heard about trust, they do this thing where like old executions get revisited when you learn new information about possible reads from edges, which like isn't that a problem if you need to randomly sample the tree because you need to know about those revisiting things, which you only know if you explored other parts of the tree? Like it is stateless, but it does like, I mean, it has the state of like its current position in the tree, and then that still informs like future exploration across the tree. So I'm wondering if that's a problem.
So trust is stateless in the sense that it only needs the information on the current stack to get future explorations. It has a special condition called maximality condition or what, which means that you can determine whether to consider this new partial order purely depend on the current what you remembered on the current stack. You do not need to consider the other branches you have already explored, but you may need the information on the current stack. So in this trust tree, it means that you need you see that different passes have different lengths, right? Although the program executions all have the same length. And we are basically only sample random paths in this tree. And whether a certain, and at each step, whether you should consider a certain RF only depends on what you have seen on the current path.
Revisiting kind of makes it a child, not a sibling.
Yeah, revisiting, yeah, we have longer passes because we are doing revisiting, but it's part of the tree model.
Let's thank the speaker.